Okay, so we're going to be going over this homework, the homework for week 7 on direct products. So in the first one, it is a visual one about Cayley diagrams, and we're going to be going over Cayley diagrams a little bit more in the class right before the mid-course test. I said we'd go through it more in lecture, but we're actually going through it more in lecture this coming week. So this top one, so what we want to think of when we take products of two groups and deal with Cayley diagrams is we are thinking of writing like copies of one group at each node of the other group, and then connecting those copies like the other group was connected. Okay. So you can see the copies of the group at each node. Okay, so here I see copies of Z3 at each node of a Klein 4 group. So I know that it's Z3 times K4. The cyclic group of order 10, you should be able to write pretty easily as a product of two groups. Using that technique of writing like what I would probably start with, well, you could do it either way. So for example, you could start with C5 and you could write a copy of C2 at every node, and then you could just connect the C5s. Sorry, connect the C2 nodes that you just created, just like C5. Okay, this one's like a little bit hard to decipher when you're looking at all of the different arrows. What I'm seeing down here is 4 copies of a red arrowed thing and 4 copies of a blue arrowed thing. And the red arrows are totally consistent from copy to copy, but the blue arrows seem to switch. Okay, so I would use that to write some candidate products and label the nodes, and then see, do these products or supposed products behave like we would expect products to? Does the fact that we have an arrow going like in a way that is consistent with the cycle here, but then kind of backwards here, does that mess up the overall product or not? Okay. In the next one, how many elements of order 4 does Z4 times Z4 have? And then the second part seems like really weird at first. Why does Z of 8 million times Z of 400,000 have the same number of elements of order 4? This seems absolutely absurd at first, but we have to go back to what we know about cyclic groups. And the number of elements of a certain order in a cyclic group is only determined by that order. And in particular, we know that phi of that number corresponds to the number of elements of a certain order in a cyclic group. So Z of 4 has phi of 4 elements, and Z of 8 million has phi of 4 elements. The only thing that would prevent us from not having Z of 4 elements of order 4 in a group is if 4 did not divide the order. Of course, 4 would have to divide the order of the cyclic group. And all of this is done under the canopy of cyclic groups. I'm assuming that the group is cyclic. This does not hold in general. Another way that you could do this, or that you could approach this, especially for the small orders, is to write out the orders of each element. If you're still feeling a little uncomfortable with cyclic groups, that's what I would recommend. But in any case, you figure out how many elements of order 4 each copy would have. And then you know that in order to have order 4 in a product, the LCM of the orders of each one has to be equal to 4. So that means really nothing for Z4 and Z4, because the order always has to divide 4. But over here, in Z of 8 million, it becomes a little bit more consequential, because, for example, we could have order 25 and order 4 in 2 elements. And then the order would be something like 100 of that element. So we have to be a little bit more careful there. So the possible order combinations that we can have are, we could have a Z, or we could have an order 1 in the first and an order 2 in the second. Sorry, let me back up. I forgot we were under 4. We could have an order 1 in the first and an order 4 in the second. We could have an order 4 in the first, an order 1 in second. We could have an order 2 in the first, and an order 4 in the second, an order 4 in the first, and an order 2 in the second, or an order 4 in both. I think those are the 5 possible cases. Okay. And then all of those would produce an LCM of 4. Okay. And the next one, we know that S3 times Z2 is isomorphic to one of the following groups. And we need to determine which one by elimination. Well, we can eliminate the first 2 right off the bat. They are abelian. This group is clearly not. S3 is like the furthest thing from being abelian. So the product is definitely not abelian either. And then what I would recommend to distinguish between the next 2 is start to look at the orders of the elements, and to narrow down even further. I always start by looking at the, say, number of elements of small orders. So the number of elements of order 2 or the number of elements of order 3 would work here as well. Okay. When I say would work here, I mean you could investigate that, not necessarily that it would give you your proof. Number 4, part A, you could do this one by just using the 1-step or 2-step subgroup tests. And then part B, if G is a set of real numbers under addition, G cross G is going to just look like the Cartesian plane that you're used to. So the diagonal is going to look literally like a diagonal line. And so that, like, the y is equal to x line. So that's where this comes from. Okay, in number 6, we want to express u of 165 as an external direct product. And for this, we need to use some of the theorems from the section. Yeah, I'm not going to focus on that too much. It's kind of an application of the theorems. To show that x to the k is equal to e for all x in u of 7 times 17, again, we need to use some theorems. So this is isomorphic to z of 6 times z of 16. And so the LCM of 6 and 16 is going to be the number, okay, there's the least number a that is going to give you this. So extending this to u of pq, it's the LCM of p minus 1 and q minus 1. 6 examples of non-abelian groups of order 24. This one's kind of fun. So I'm not going to ruin all the fun and just give you a bunch of groups. But what I would start to think of is, like, what groups are in your catalog. So we have dihedral groups, we have permutation groups, and permutation groups have orders that play really well with 21. So their orders, or sorry, 24, their order is like 4 times 3 times 2 times 1. Orders like 3 times 2 times 1. Things that are a lot like 24 or very close to 24. I think I keep saying 21. I don't know why. I think it's getting late. So think about 24. Also, don't forget about the quaternion group. The quaternion group has order 8, and 8 divides 24 as well. So any of these things divide 24. And then when you match them up with the right other group, so for example, you have quaternion is 8. 8 times 3 is equal to 24. So you can do Q8 times Z3. That'll give you a non-abelian group of order 24. Okay, so those are a couple of hints. Basically use what you know. You should not go out and try to find your own group for this. That's a warning. Don't try to define your own group. Use what you already know. Okay. Compare the number of elements of each order in D6 with the number of each order in D3 cross Z2. So D6, those elements you should be able to do from a Killy diagram or a Killy table, or kind of things that you know, basically. Remember, flips have order 2. And then the rotations act like the cyclic group in terms of orders. And then D3 cross Z2, you can find the orders in a similar way using the LCMs. So you can find the D3 orders, and then the D3 order will have the order of a D3 element cross a Z2 element will just depend on whether it's matched up with a 2 as a second one or a 1 as the second element. Okay, so the order will be the LCM of the order of the first and the second. I feel like I was kind of going around in circles there, but I think I just better stop. In exercise number 10, we're back to the automorphisms of Z of 105. So in class, we went over why the automorphisms of Z of 105 are isomorphic to U of 105. And U of 105 is, well, U is, 105 is equal to 3 times 5 times 7. So U of 3 times 5 times 7 is isomorphic to Z of 2 times 4 times 6. Or that is Z of 2 times Z of 4 times Z of 6. That's the right way to say that. And so we can find the elements of different degrees in the same way as we found the elements of different degrees earlier when we were dealing with products of cyclic groups. Okay. So I think that I will stop there. This was a much more difficult section to talk out the hints of because there were a lot of moving parts. So I hope that this helped at least just a little bit.